verifying the ideality of urea ethanol solution.
Presented by Zach Brenner,
Harley Estes,
Azrae Johnson,
Matthew Kelly,
and Matthew Nelson.
The purpose of this experiment is to verify the ideality of urea ethanol solution by using the heat of fusion to predict the solubility for solids and liquids. To carry out our experiment, we compared the behavior of temperature variation with mole fraction to the theoretical equation for an ideal urea ethanol solution. Before starting this experiment, make sure you have proper safety attire in the working lab zone. Equipment needed for this experiment includes 2 Erlenmeyer flasks, 1 filled with ethanol, plenty of urea, 5 test tubes with a test tube rack, a ring stand, a hot plate, a beaker filled with water, a thermometer, and a clamp. To begin this experiment, we need to zero out the vessel that will contain our ethanol. Now that we have zeroed out the vessel for the ethanol, we want to measure out 1 milliliter of ethanol and put it into the vessel and determine the mass. For this, we will use the density formula, mass divided by volume, to find the density of our ethanol and compare it to a literature value. Now we need to measure the 1 milliliter volume of ethanol, and it turns out to be 0.802 grams. Using the density formula, rho equals mass divided by volume, we can find the experimental density of our ethanol, which is 0.802 grams per milliliter, and we compare it to the literature value, which is 0.789 grams per milliliter. The procedure for this experiment is to have 5 clean and dry test tubes. We will use a set amount of urea, in our case it is 0.5 grams, and we will change the amount of ethanol in each test tube. Also, the water bath for this experiment will need to be at 80 degrees Celsius. After dissolving the urea and ethanol, we will remove the test tube from the water bath and let it cool in an Erlenmeyer flask. While the urea and ethanol solution cools in the Erlenmeyer flask, we will continue to mix it until crystals will form. At that point, we will record the temperature. We will also run the experiment for every test tube. As previously stated, we want to use 0.5 grams of urea for each test tube. We now have 0.5 grams of urea in each test tube. It's time to put in the ethanol in each test tube. At increments of 0.5 milliliters, test tube 1 has 2 milliliters and test tube 5 has 4 milliliters. In this case, for test tube 4, we have 3.5 milliliters to pour into test tube 4. To dissolve the urea in the ethanol solution, we will put the test tube in a hot water bath at 80 degrees Celsius. We will continuously stir the solution until all the urea has dissolved. Once the urea has dissolved in the ethanol solution, place the test tube in an Erlenmeyer flask so that the temperature decrease is minimum and we can get an accurate reading when the precipitant forms. Also, continuously stir this mixture throughout this process.
Eventually,
after all test tubes were heated and then cooled down to form a precipitant, the temperature was recorded and placed in a table. Now that we have the recrystallization temperature for every test tube, we need to find the mole fraction of urea, which was easily done in Excel. For this mole fraction of urea, we want to create a graph and find the linear regression of ln of x, which we will consider the mole fraction of urea, versus 1 over temperature. Here's the graph of the ln of the mole fraction versus 1 over temperature. Note that the linear regression r squared is equal to 0.79. In conclusion, urea and ethanol can be considered an ideal solution because the experimental regression is 0.79, which is near the theoretical regression of 1.